There are a number of definitions of acids and bases, all of which are correct, but some include more examples of acid-base behaviour than others. The dissociation of water is an example where all three definitions of acid-base behaviour can be applied. Arrhenius would have described this reaction by saying that a water molecule dissociated into hydrogen and hydroxide ions, therefore it was acting as both an acid and as a base. Bronsted and Lowry would have said that one water molecule would act as an acid by donating a proton to another, which in turn would accept it to form a hydronium ion, so therefore it would be acting as a base. Lewis would have described that process in terms of the proton accepting a pair of electrons to form a dative or coordinate bond, so the water molecule donating a lone pair to the proton is acting as a base. In these reversible reactions, we can identify pairs which differ by a proton, known as conjugate pairs. This water molecule will accept a proton to form the hydronium ion, therefore acting as a base. That will release a proton to form water again, and in doing so will act as an acid, the conjugate acid. If you have a very strong conjugate acid, or base, like we do here, then the equilibrium lies to the left. In other words, water is neither a very good acid nor a very good base, which is hopefully not a surprise. How well did you listen to the last slide? Identify the types of definition which are appropriate, and next identify the conjugate pairs. Click Submit to move on to the next question. pH is a way of measuring acidity and uses the log scale. A log scale allows us to compress very large or small numbers into numbers that are easier to understand. Notice in the table the relationship between the number of decimal places, the power of 10, and the log when we use log to the base 10. Take a moment as well to look at this picture. You can click to see a larger version. The image shows what happens if you take the log of a distance. The diagram shows detail over a wide range of distances. We measure acidity by concentration of hydrogen ions in solution. These concentrations are often very small and they can take a wide range of values, just like the distance scale in the universe picture. So we use logs for convenience. pH stands for minus log to the base 10 of the hydrogen ion concentration. We take the negative such that pH is usually a positive number itself. P just means minus log to the base 10 of something. So for example, if we had a solution containing 1 times 10 to the minus 3 molar hydrogen ions, its pH would be 3. The dissociation of water can be written in two ways. It's often written in a simplified form, as you see here on the right. The reaction is endothermic, as you might expect. We can also write a Kc expression, and if you're not sure how to do this, take a look at the equilibrium package. The equilibrium lies so far to the left that the equilibrium concentration of water effectively remains constant. For simplicity, the water is removed, leaving the ionic product of water. We give this its own special equilibrium constant, Kw, and the value is 1 times 10 to the minus 14 mole squared decimeters to the minus 6. In pure water at 298 K, the concentration of H plus is 1 times 10 to the minus 7 moles per decimeter cubed. The concentration of hydroxide ions is the same. As long as there is the same number of each, the solution is neutral. Take care though, temperature can affect equilibrium constants, so whilst the concentration of hydrogen ions can change, resulting in a change of pH, the solution will still have an equal number of hydroxide ions, so will remain neutral. On the next slide, there are a few questions to test your understanding of this. Test your understanding of Kw with these questions. Bronsted-Lowry acids dissociate, i.e. break up, in solution to release protons, but not all acids dissociate in the same way. We describe an acid that is highly dissociated as being strong. The strength of an acid does not tell us about its pH, unless we know how concentrated the acid is. It's possible to have a dilute solution of a strong acid that does not have a very low pH. It's important to be clear in the use of the words strong and concentrated in this context. We make the assumption that strong acids completely dissociate, so therefore the concentration of protons will be the same as the concentration of the acid. If we have a 0.25 molar solution of hydrochloric acid, a strong acid, the concentration of protons would be 0.25 molar as well. Be careful though, as for diprotic acids like sulfuric acid, which yields 2 protons for every acid molecule, the concentration of protons would be, in this case, 0.5 molar. pH is minus log to the base 10 of the hydrogen ion concentration. The concentration of H plus from the dissociation of water is tiny compared with that of the acid, so we ignore it. This gives us a pH of 0.6. So to summarise, with strong acids, ignore the H plus from dissociation of water and assume that the H plus is the same as the concentration of the acid. Not forgetting, of course, that you may need to double that number for a diprotic or treble it for a triprotic acid. Try your hand at this question. Click Submit to move on. This question is a little bit trickier and is the first to require more than one step in your calculation. Calcium hydroxide is a strong base, so you can assume complete dissociation, but how many moles of hydroxide ions will you get from 1 mole of calcium hydroxide? When you know the concentration of hydroxide ions, you can use Kw to work out the concentration of H+, before working out pH. It's really important not to round off too many significant figures from the answer to each step, especially when handling logs, because small errors can quickly throw you far off the mark. Look out for this later on if you think you followed all the correct steps and still get an incorrect answer. Some acids do not dissociate much at all. Most of the molecules in solution remain intact. We call these weak acids. They can be concentrated or dilute just like strong acids, so it's quite possible to have a weak acid with a lower pH than a strong acid, which may seem counterintuitive at first. Because the acid only partially dissociates, we can't make the same assumptions. We can write an equilibrium constant for the dissociation as Ka. Because Ka tends to be very small for weak acids, we can assume that the concentration of acid at equilibrium won't have changed appreciably from the concentration of acid that went into the system, so we just assume it remains unchanged. Just like before, we can ignore the H+ concentration from the dissociation of water, and we can assume that all of the A- has come from acid dissociation, so that will be the same as the concentration of H+. So let's put this into action. If we have some 0.25 molar ethanoic acid, and we want to work out its pH, we'll want to get at its Ka first. Now let's apply our assumptions. If H+ equals A-, we can just simplify that to H+ squared, and we can assume our acid concentration is still 0.25 molar. Rearranging and taking the square root, we get our concentration of H+. The last step is to convert this into a pH. Try some weak acid calculations for yourself now. The larger Ka is, the stronger the acid. If Ka is larger, it follows that the equilibrium has moved to the right, or dissociated side. In order to shift the equilibrium right, we need to slow down the backwards reaction, and one way of achieving this is to increase the stability of A-. Taking ethanoic acid for example, we're interested in the relative stability of the molecule and its ionized form. The stability of the ion is helped by a process called resonance, through which the charge is spread over more than one atom. This arrow shows a pair of electrons moving from the oxygen atom to the bond. The oxygen atom accepts a pair of electrons from its double bond. If you're not clear on why a pair of electrons is being moved here, even though there is only a 1- charge, take a look at the basics of mechanism activity, or draw out a dot-cross diagram to help visualize what's going on. The result of this is the same structure with the electrons moved around. No chemical reaction has occurred here. We use a double-headed arrow to denote this type of resonance. Of course, the reverse process can occur. In reality, these arrows are a simplification and show two extremes. The negative charge is distributed over the three atoms, and so could be represented by a dashed line, which may better represent the fact that the charge is in an extended molecular orbital over these three atoms. You can find out a little bit more about molecular orbitals in the Basics of Mechanism resource. If we can increase the stability of the ion still further, pKa will drop. One way is to use highly electronegative atoms to pull that negative charge towards them, which in effect distributes it over even more of the molecule. We call this an inductive effect. Although we don't talk about the CH bond as being polar, there is a small difference in electronegativity, and methyl groups can display a positive inductive effect. In this case, pushing charge towards the area where there is already a negative charge, and that's going to destabilize it, making A- less stable and causing pKa to rise. Another effect results from the special stability associated with molecules that have an electronic structure similar to benzene. We call this aromaticity. In the same way that adding a proton to benzene would disrupt its aromaticity and would be highly energetically unfavourable, we can look at what happens when we add protons to other compounds. Have a look at these two compounds, which we might expect to act as a Lewis base just like ammonia or an amine. We can examine their behaviour as a base by considering the pKa of their conjugate acid. Match up the compound with the correct statement and click Submit to carry on. Pyridine acts as a base, but pyrrole does not. The difference between them is staggering. Consider first that sulfuric acid has a pKa of -3, so the conjugate acid of pyrrole is 10 times stronger an acid than sulfuric acid is. Another way of putting it is that there are about 9 powers of 10 difference between a pKa of -4 and of 5. So pyridine is about 2 billion times better a base than pyrrole is. To understand why, we need to think why the conjugate acid of pyrrole is so unstable compared to that of pyridine. Here we have 4 carbons in the ring, each with a spare electron in a p orbital, which contributes to an extended pi system, just like benzene. If you're not sure what a pi bond is, you should look at the resource on Basics of Mechanism. Benzene has 6 electrons in its ring, however, so for pyrrole to be isoelectronic, i.e. to have the same electronic structure, 2 electrons must be contributed from the nitrogen atom to the system. These come from the lone pair. This makes the compound aromatic. If the lone pair were to act as a base and become a bonding pair, the aromaticity would be lost. Pyridine has an extra carbon atom in the ring, which contributes an extra electron to the pi system. Nitrogen now only needs to contribute 1 electron to make up the 6 that are needed. Its lone pair is not involved and can still bond to a proton to show Lewis base behaviour. This means that the conjugate acid of pyridine is still aromatic, so is vastly more stable than the conjugate acid of pyrrole. Given the specificity of its enzymes, our body must maintain a stable pH in order for us to be able to survive, but we regularly consume food and drink that would alter our blood's pH. A mixture of chemicals known as a buffer can be used to resist changes in pH. A buffer solution consists of a weak acid and its salt. If acid is added, the salts can absorb excess H+, shifting the equilibrium left and forming more molecular acid. If base is added, the weak acid can dissociate to replace any H+ that was absorbed. We can't make all the same assumptions about Ka that we were able to when we looked at weak acids. We can still treat all of the H+ as having come from the acid, and because the acid is weakly dissociating, we can still assume that the concentration at equilibrium remains unchanged. But we can't assume that all of the salt, or conjugate base, came from the acid dissociation, because we've thrown in a lot more ourselves. The amount we would add is likely to be a lot more than the tiny amount coming from the dissociation of the acid, so we can just treat this A- term as being the same as the concentration of salt or conjugate base that we've put in. So here are our key points. I'm going to rewrite HA as acid and A- as conjugate base for the moment, so it's a bit clearer what I'm talking about. We can then rearrange and write the expression in terms of H+. We have our Ka multiplied by the ratio of the acid to the conjugate base. This means that the Ka, or more specifically the pKa, will give us the starting point for the pH of our buffer. It's a bit like the coarse focus on a microscope. Once we have our ballpark pH, the ratio of the acid to the conjugate base can act as a fine focus to tune the pH to exactly what we want it to be. If these two concentrations are equal, then this term will be 1, and H+ will equal Ka, so the pH will be the same as the pKa. Let's look at an example of a titration to see this from another angle. We start off with a solution of ethanoic acid. In our conical flask we have particles of acid, water and a very small amount of dissociated H+ and A-. The H+ is making our solution weakly acidic. We start to add some sodium hydroxide, which is a strong base, so the sudden rush of hydroxide ions can quickly reduce a comparatively small amount of H+ from the acid. However, as this happens, we start to produce the salt of the acid that has so far been neutralized, in this case sodium ethanoate, and this acts in combination with the remaining acid to act as a buffer. As such, the rate of increase of pH drops as more sodium hydroxide is added until we run out of acid, and our solution is neutralized. At the equivalence point, we have only salt and water in the solution. Sodium ethanoate is slightly basic, so the equivalence point is not at pH 7. As we continue to add sodium hydroxide, the pH rises until we're limited by the concentration of the sodium hydroxide itself. If we go back to the point at which we've added half of the volume of sodium hydroxide needed to neutralize our solution, think about what will be in solution here. On the left we have all acid and very little conjugate base. On the right we have all conjugate base, or salt, and no acid. Here their concentrations are the same. This means that the acid-base term becomes 1. So, H+ equals Ka and pH equals pKa. If you know the pKa of a compound, you'll then know the pH at which it will be 50% dissociated, and that will, for example, affect its solubility. How much sodium methanoate would you need to add to 500 cm³ of a 0.1 molar solution of methanoic acid with a pKa of 3.75 if you want to make a buffer solution with a pH of 3.84? Okay, this one's a bit trickier. You've got 200 cm³ of a 1 molar solution of ethylamine. How much hydrochloric acid, 0.1 molar, are you going to need to add to make up a buffer solution with a pH of 11.5? So that was quite a tricky question. Here's our buffer equation again. We have our amine as our conjugate base in our previous examples, and the acid is going to be the protonated form of the amine. We can rearrange our buffer equation as written here. The ratio of the acid to base in the buffer solution is going to be equal to the concentration of protons divided by Ka. We can work out our H+ and Ka from the pKa and pH that we've been given. That will give us a ratio of 0.158. The next thing to think about is how much A and B individually are going to be. We start off with 0.2 moles of amine, but we want to work out how many moles of amine are going to be in the buffer solution after we've added our acid. We can write this as a simple expression. We also know something else about our mixture, as we've already said. We can write that in terms of A as well. That means we can combine our two equations, like so, and work out what B is. Once we have B, we can plug B back into either of the two expressions at the top to work out what A is. So now we have the number of moles of acid we want. Given the fact that we have its concentration, we can work out our volume of acid that we want to add, and that will give us our answer. We want to add 274 cm³ of our 0.1 molar acid to make our buffer solution. There's another way of working this out that's a bit shorter and uses logs and is probably a little bit better, but not as simple as this way. If you want to have a look at that, you can click on this link. That concludes this activity. Have a look at chemguide.co.uk if you want to learn more about acids and bases.